Hello and welcome to another topic in chemistry. If you are watching this video on the first time it was assigned, it is June 1st, 2021, Unit 12, the first day of Unit 12. And the topic that we're focusing on is Le Chatelier's principle and KEQ. Go ahead and set up your focus notes. If you're watching this video for any other time, any other reason, I welcome you. I'm excited to talk about chemistry with whoever is listening. So for your focus notes, here's our topic. And then the essential question that we will be answering in today's video notes is, what is Le Chatelier's principle? And how do I write an equilibrium expression for a chemical reaction? And just to make the connection, KEQ is your equilibrium expression. So those are the two things we're going to be able to figure out by the time we are done with this video lecture. All right, pause the video if you need more time setting up your notes. Otherwise, let's get into it. So the first thing that we need to know is that our focus in this unit is about a reversible reaction. And a reversible reaction is when the reactants go to products, which is what we've usually talked about, but it turns out that also the products can turn back into reactants. So it's a reversible chemical reaction. So that can happen. So here's a visual example. So you can have nitrogen dioxide gas that will produce dinitrogen tetroxide gas. However, this also decomposes into two molecules of NO2, and it goes back and forth, back and forth. And it turns out that if you were to mix these in a closed setting, you could actually see the colors change. So this is what this is representing. So you can see that you've got a sealed tube in here, and then as it is allowed to react, so it's brown when it's NO2, and then as it reacts more, like as it gets colder, then it turns into the colorless, and then it goes back this direction and turns brown, and then it goes back and forth. So this would be based on temperature, would create, well, which one of these is more likely to form. So visually, you'd be able to see it, brown versus colorless, and that could go back and forth, back and forth. So sometimes this breaks apart into that, and sometimes these two molecules combine together, synthesis, to make this. So that's the idea of a reversible reaction. Your reactants turn into products, but also your products can go back and make the chemicals that we had at the beginning. All right? So there's also something referred to as chemical equilibrium that I want to refer to. And this is when, if you have one of those reversible reactions, you have the same amount of reactants turning into products as the amount of products turning into reactants. So they're happening at the same rate. It doesn't mean you have the total same amount of both, but it means that the amount turning into a product and the amount of product turning back into reactant, that's happening at the same pace or speed. Think of that as same rate. So that is what chemical equilibrium is known as. And when we have reached chemical equilibrium, we can write something called an equilibrium constant. And that is, the symbol for that is a capital K and then EQ. So the K value is a letter we usually mean for constants, and then EQ means, oh, this is the equilibrium constant. And the way it looks is this. Let me give you a generic setup. So imagine that this was a chemical reaction. Capital A, capital B, capital C, and capital D are all chemicals, and then the lowercase r, lowercase j, lowercase f, lowercase x are the coefficients in a balanced equation. So if this is any version of a chemical reaction, it doesn't just have to be two reactants and two products. It could be one reactant, it could be three, it could be five products, it could be one. So the point is that this is just a generic version of a reversible reaction. The way you write the equilibrium constant is that you put the products on top. So in this case, it was capital C raised to its coefficient. So C raised to F and then D raised to X. So again, this could be a chemical formula like H2O. And then in the balanced equation, there was two of them. So this would be like H2O raised to a 2. And that's actually not a great example because H2O would be a pure liquid, so then it wouldn't have a concentration. And we'll talk about that actually on our next slide. But the point is that generally you put the products on top and you put the reactants on bottom. So that is always the same, products on top, reactants on bottom. But it turns out that it has to be something that can have a molarity. So these would be things like solutions and gases, things that can mix together to have moles of solute and moles of solution, that kind of idea, or moles of solute and then liters or liters of solution, since we're talking about molarity. So these brackets are not just generic parentheses. These brackets, remember, mean molarity. We talked about that a little bit in our acid-base unit. So products on top, so in this case it was C and D, raised to their coefficients, and then this would be the reactant. So A and B raised to their coefficients. That is how you write an equilibrium expression. So then you could calculate the equilibrium expression or the equilibrium constant by knowing the molarities, and then you would raise them to whatever coefficient they had in the balanced equation, multiply those, and then divide by this. So that's the general idea. So we're seeing what is the general concentration of your products divided by the general concentration of your reactants. That's the idea there. So a little bit more about that. So as I mentioned, this, remember, is a molarity. So if you have a pure solid or a pure liquid, they're not going to change their concentration because they don't have a moles per liter of solution. They would just have moles, right? So no matter how much you have of them, you're always going to have the same concentration. So then pure liquids and pure solids are left out. You don't include them. So let me go back to this for a second. So if this had been a solid, this would have just been left out. You would just have C raised to the F on top divided by your A and B on the bottom. So just realize that. You would just exit out. It was like it didn't exist, and you would not write it in your KEQ or your equilibrium expression. Only aqueous or solutions and gases are included in your KEQ expression. And then the other thing that's useful is that if you see a KEQ greater than 1, you know that in that reversible reaction, you are more likely to have the products forming. If the KEQ is less than 1, you will know that in that reversible reaction, you are more likely to have the reactants be favored. And that can be really important for some type of industrial reaction where either you want to produce products, then you know to pick concentrations so that it will be force it to have a KEQ greater than 1 so that products are favored, or the opposite. If one of your products is dangerous or is a pollutant and you don't want that reaction to happen, so even though it's a reversible reaction, it's going to happen on its own, you can choose concentrations so that the reactants are favored, so that you'll get a KEQ and an equilibrium expression less than 1, or an equilibrium constant. The expression is that the setup of the math equation. All right, so that gives us a little bit more detail, like the quantitative things we use with reversible reactions. All right, what I want to talk about next is more the qualitative piece, and that is known as Le Chatelier's principle. The general rule of Le Chatelier's principle says, if a stress is applied to a system that has already been in equilibrium, the system will adjust to relieve that stress. So the idea is that a system would be a chemical reaction, and if you do something to mess up that balance, the system adjusts itself to get back to being balanced. So think like a teeter-totter, right? So right now, there's way too much on this side of the teeter-totter. So what we could do is we could add more on this side of the teeter-totter, and it would go back to being balanced. So if we think of a balanced equation like a balanced teeter-totter, then that's the idea. So we're going to talk a little bit more about the stresses that we might apply to a chemical reaction, but just know that the general idea is think of a balanced equation as like a straight across balanced teeter-totter. And so if you mess up either side, the reactants or the products, by doing different things, that system will automatically try to get back to being balanced and to relieve that stress. That is known as Le Chatelier's principle. Let's get into some examples then. There's 3 different ways we're going to talk about that we can stress out a system. The first one is going to be changes in concentration. Okay, so imagine this is your balanced equation. So this is some sort of reactant, this is some sort of product. Right now it's at equilibrium. If I add a reactant, that will push the reaction towards the product. Because think of it, if this side is too heavy, the reaction is like, oh, I need to make more of this to get it back to being balanced. So if this side goes down, I need more of this to get it back to being balanced. That's the idea. So adding a reactant will make the reaction switch over to make product to get it back to being balanced. If you remove a reactant, that means that this side would be too light. There's not enough of it. So then the products would shift back to the reactant to make more reactant to get this being balanced. So if this side was too light, I need more of it. So it would have to shift back towards the reactant side. If you add a product, it's going to go in the direction of the reactant. So if this side was too heavy, so it goes back this side, I need more on this side, so I shift back to the reactants. So there's that back and forth teeter-totter kind of idea. So again, think of this as a balanced equation. If you have too much product, it would shift back to the reactant to get this to being balanced. So adding a product will shift back to the reactant side. And if you remove a product, then the reactants are like, we need to make more product. And then if you remove more product, the reactants are like, we have to make more product. And so that's a trick that often is used in industrial reactions. Like, for example, if you're trying to produce ammonia for fertilizer from nitrogen and hydrogen, as the ammonia forms, if you remove it, the nitrogen and hydrogen are like, we have to make more. We have to get that balance. And if you remove the ammonia, it will make more. Now, eventually, you might stress out the system so much that it cannot get back to balance on its own. And then you would have to sort of start over. You would have to remeasure out your reactants and then make your products, get it to its own equilibrium, and then you could go back and do this trick. So changing the concentration, meaning how many reactants and products do you have? If you add more reactants, it shifts to products. If you have too much product, it shifts reactants. If you take away reactants, it shifts to the reactants. If you take away product, it shifts to the product. So trying to always maintain that equilibrium. That's, remember, what a reversible reaction tries to do. Another type of stress is you can change the pressure, but this only works for gases, all right? So that's super important. So it only affects gas products and gas reactants. If you are dealing with liquids and solids, they are not very much affected at all by pressure, so that's not going to matter. So think of like, well, what side has high pressure, what side has low pressure, and then it will shift to whichever side is lower to release that stress. So imagine I have this. This was that brown and colorless example I gave at the beginning. So if I have, in this case, 2 moles of gas on this side and 1 mole of gas on this side. Well, right now, this already has more pressure because there's twice as many moles of gas particles. So if I increase the pressure of this whole thing, there would be so much pressure on this side, it would shift to the products to relieve that extra pressure. So you still think of it as like back and forth, like a teeter-totter, but think of it as what has too much pressure. So opposite, if I decrease the pressure of this whole reaction, there would be not enough pressure like normal. So then it would shift to the product side, which has more pressure to start with, to try to create that balanced amount of pressure at equilibrium. So think of it as like the same idea of concentration. If you have too much pressure, it shifts to whatever side has less pressure. Or if it has not enough pressure, it shifts to whatever side has more. Here's another one. Take a look at this. So I've got ammonium chloride and then ammonia and hydrochloric acid. Okay, well, first of all, we need to notice that this is a solid. So if I change the pressure, the only side that's going to be affected is this side. So if I decrease the pressure, I would shift to the product side because both of these particles of gases would be forming pressure. If I increase the pressure, then this will want to relieve it and it will want to go to this side. But releasing and changing the pressure doesn't affect this part of the equation at all. And then here's another one. So first I noticed that all of these are gases, but then this has 2 moles of gas because of the balanced equation. But look, this also has 1 plus 1. That's 2 moles of gas. So in this case, this is at equilibrium. When you change the pressure, there's no change. It will always have the same amount of pressure on both sides. So if I decrease the pressure, it will have the same amount of pressure on both sides. So this is an example where you wouldn't really be affected. So changing the pressure would not stress out this equation. So something to also think about. The third type of stress that we can have is affecting the temperature. So then you can just think of heat as either a reactant or a product. It acts just like those changes in concentration that we've talked about already. Remember, an endothermic reaction is when heat is a reactant. It's going in to the system, and the reactant, the delta H value is positive. An exothermic reaction, heat is exiting the system, so the delta H value is negative. So a little review from Chem A, that we measure the heat of a reaction with delta H, the change in enthalpy. So if there's heat going into the system, that's endothermic. If heat is leaving the system, product, then it's exothermic. And then that will actually affect your equilibrium constant. So something to realize that if you have an equilibrium constant, it's temperature dependent. So if you're doing a calculation with KEQ and you change the temperature, you're going to need to find a different KEQ or calculate a new KEQ. All right, take a look at this example here. So first of all, I noticed that they're all gases. Okay, I noticed that this has 2 moles of gas and so does this. So pressure is not going to change very much. But I also noticed that this is an exothermic reaction because the delta H is negative. So if I heat up this product, this side already has a lot of extra heat. So it would shift to the reactant side to relieve that stress because there's too much heat. Or the opposite. If I cool this down, the reaction is like, oh, we're not the temperature we're supposed to be. I need more heat. So then it would shift to the product side because this is the side that has the heat on it. And I know that because it's a negative delta H value, meaning that heat is really just a product. So then the opposite, this is a positive. This decomposition reaction only happens if heat is added. So that means that this side is where the heat would be. So again, if I heat up this whole thing, this side would be too hot, too much. It needs to shift and it needs to break down and make product. Or if I cool this thing down, then that means that these gases aren't going to want to stay gases. They're going to want to shift to the reactant side to warm themselves back up. So that's the idea. So think of heat as either a reactant or a product, whether it's endo or exothermic, and then you can still just think of that teeter-totter example. Whatever side doesn't have enough heat, it would shift to that side to get itself back to being balanced. So 3 types of stresses we think about are changing concentration, like actually pouring in more reactant or product, changes in pressure when you're dealing with gases, and then changes in temperature when you're dealing with endo or exothermic types of reactions. That is Le Chatelier's principle. And that brings us to the end of this first day of equilibrium chemistry. So I noticed that I didn't have you write COSTA questions during the notes. So go back and process the notes, write one question for each level, 1, 2, and 3. Write a cinquain summary, something to just get you thinking a little bit more about this. Remember, a cinquain is a 5-line poem that's based on syllables. There's 2 syllables in the first line, then 4, 6, 8, and 2 in the last line. And the purpose of this cinquain is to make you think a little bit, think about Le Chatelier's principle and shifting back and forth. And there is a place in your notes handout that goes with this video where you can write in that cinquain. There are equilibrium readings that are part of your notes handout that went with this video. Those last 2 pages, I think they're pretty interesting. One's about eggs and chickens, and then one is related to a war story, kind of. So anyway, there's some readings just to make some connections in our world about equilibrium processes. And then I do have a practice assignment on equilibrium expressions where you write them and calculate them. So that's something you could start and come with questions the next day. You could also be finishing any missing work as we are nearing the end of our trimester if you are watching this video when it was originally assigned. So take care, finish the rest of these things in the notes handout, COSTA questions, write your cinquain summary, and then this is do the readings, and then this is a separate assignment, a practice assignment that gets you started. It's 1 page just to kind of practice writing these KEQ values and also doing some calculations. And that's it. That brings us to the end of this video notes. Thanks so much for listening. We'll talk to you later.